So today I'm going to talk about how to use software verification techniques to help hardware verification. So basically, okay, this is a very messy figure, but basically what we see here is each data point represents a unique hardware developed by one group, either from academia or industry. So basically, the main idea here is like the explosion of AI now leads to the rise of custom hardware, which have dedicated architecture for specific applications with high energy efficiency, right? But designing this hardware architecture is not just walk in the park. You need a lot of low-level knowledge to understand what's going on in the hardware, and then we can explore parallelism or other optimizations. In the meantime, we also need to understand the software algorithm we try to map onto this hardware, which usually like software engineers will develop like rewrite techniques, try to optimize the performance of software. So they are quite isolated, right? But like Alan Kay said, is like people who are really serious about software, they should make their own hardware, because everybody care about software hardware co-design nowadays. This is how we make best performance. So this naturally brings a new technique called high-level synthesis. So it's an automated technique that translates software algorithms into efficient hardware systems. When I say efficiency, it means smaller, faster, and low energy and secure hardware. So typically the users or the designer is going to write software algorithm or specifications in C or C++, which is software language, and then the tool automatically generates hardware implementation in RTO languages. So, but I'm a negative person, so I'm going to ask one question. Does that actually work? Does these tools have bugs, right? So even for industrial tools, the comments like, we're seeing the rising use of C or C++ into these RTOs, but we still don't know how much we can trust these tools, right? So if we go back to the literature, there are works to try to fuzz these tools, and the conclusions are not surprising. It has bugs, right? So then, while these tools are already used by industrial partners, then the question is, how do we know whether my hardware is actually correct? How do I identify these bugs? So let's go back to see what happened in industry, right? Like Intel. So we got a hardware architect who knows exactly what we want to build, and they write this high-level architecture in software languages, and we call this synthesis tool to generate the exact hardware implementation. And then this hardware design is passed to verification tools to verify whether this is correct. But that's not a complete story. We also have verification engineers who has to read this messy code and understand what's going on, and write these low-level hardware specifications, and will interact with verification tools to verify the hardware design is actually what the company needs, right? So, and it turns out it's actually, verification is complicated. I think everybody here knows. So usually each one architect is going to pair with 5 verification engineers, and during the whole development time, 60% of time has been used for verification. And if we look at these two phases, right, it's not really fair, because verification engineer has to read whatever through at them, and they are usually not friendly. But our hardware architects have the freedom to write whatever they want. They are the person who have fun, right? That's not really fair. So we propose there should be a new way to develop hardware. So what we see here is the hardware architects are the person who knows most about their designs. So we think, what if they could also write high-level specifications while they are writing their designs in software language, right? Ideally, like, in Pharmacy or Daphne, so these specifications are verified in software with their design. And it would be nice if we have this tool, right, automated tool, to translate these high-level specifications to the hardware specification that can be picked up by the verification tool to do hardware verification. And in practice, these hardware specifications are not directly accessible by the verification tools because they are often quite complicated. Then we could add additional properties to guide the proof to make it pass in the verification tools, even they are correct and complicated. Another interesting is that these specifications are written by the architects, which we assume they are correct, right? So which means any hardware design that pass these specifications are good designs. So even if these synthesis tools have bugs and generate faulty designs, we could apply automatic techniques such as LMs nowadays. People don't trust, but we can apply these techniques to rewrite this low-level hardware. As long as they pass this specification, we could see this as a pass the guards we have to generate correct design. So the project has been going on very well. Thanks for VeTSS to fund it. So to make it possible, we have 1 paper that is currently under review and 2 in preparation. And beyond research, we also got something interesting. We have 1 PhD student co-supervised by Elizabeth Polgring here, who has worked at Amazon on a similar topic for real hardware designs. And we are now collaborating with them on verifying their commercial hardware accelerators, like the Trinium ML accelerator. Cool. Any questions?
By low level, do you mean like the netlist, or do you mean system Verilog or something like that?
System Verilog, yeah.
Okay.
Okay. Were there any others? If not, we'll move on to the next
one. I'm going to quickly through technical slides. Yeah.
Yeah. Okay. Thank you very much. We have Frederick, who will be talking about probabilistic precision tuning.
Hello, everyone. So this project, funded by VeTSS, is joint work with my PhD student at Queen Mary and my postdoc, who's here in the audience, Hamza, who was funded by this project. So what is probabilistic precision tuning? So I'm just going to give you a quick context. This is the kind of thing I'm going to talk about. So I'm looking at the code that is at the interface between sensors and more serious software. So maybe just the API, the code that's closest to the sensor. Okay. And typically this code is very compositional, very modular, small functions with not a large number of variables. So from a formal verification perspective, an ideal candidate to have a look at. Okay, and if you've seen the robotaxis that are being trialed in London, you will have noticed that they look like Mars rovers. They're covered in sensors. So this kind of code base is going to be increasingly important and is obviously safety critical. So I think it makes sense to look at these small pieces of code. So this here, I'll zoom in on this. This is part of a library for inertial measurement units. So that's accelerometers, gyroscope, and magnetometers. And essentially, it's what you have in your mobile phone that tells your mobile phone in which direction it's oriented. Okay. And what it does is typically it manipulates vectors in 3D and quaternions to perform rotations. So it's quite small number of variables. And of course, when you talk about sensor data, you're talking about noisy data. By definition, whenever you measure things, you have an element of error. So the sensor data is by definition probabilistic data. Okay, and most importantly, this probabilistic data is usually quite well modeled. And a good example of that is GPS data. GPS data, the error of GPS data is very well modeled, because the military needs to have extremely precise description of this noise. But for civilian use, a very good model of GPS data is that the error is a Gaussian. So in Cartesian coordinates, that's what the error of a GPS reading looks like. And I like this other picture here, which is the same noise, but in polar coordinates. And it shows you that as the crow flies, the distance between where you really are and your reading is very, very unlikely to be small, because that's the dip in the middle. So statistically, you're likely to be some distance away from your reading. Okay, so this, just to say that sensor data is noisy, and we typically can model this noise very well. Okay, so that means that all these little programs that manipulate the sensor data, they are probabilistic programs. We can model the input of these programs. Okay. So this is going to be my running example. It's a little piece of C++ code, which has all the features that I'm going to want to be able to deal with. namely if-else statements, arithmetics, and square roots. And if I can do that, I can do a lot of I can tackle a lot of the programs in these libraries. Okay, the inputs have known distributions, and so we can ask questions like, what's the distribution of the outputs then? If I know the distribution of the input, can I describe the distribution of the output? I can also ask the question, what's the distribution of the rounding errors? Because obviously all of this is all these arithmetic operations are being performed in floating point arithmetic. So that introduces rounding errors. So I can ask the question, what is the distribution of these rounding errors? And this brings me to the question of probabilistic precision tuning. If you're on an edge device, you always want to find the floating point representation that is the most economical. Okay, so we can ask the question, what is the most economical floating point format which ensures this kind of guarantee that the probability that a rounding error is greater than a threshold that you choose as a developer is smaller than a probabilistic threshold that you choose as a developer. Okay, now why does it make sense to think of this question? Well, for a start, the traditional answer to what's the worst rounding error I can get is a worst case scenario. And when you have data that has a distribution, an input distribution that is unbounded, your worst case error is always going to be infinite. So it's essentially useless. Secondly, this input information is actually interesting. It tells you where the inputs are more likely to be, and therefore it's going to tell you where the rounding errors are more likely to be. If you go for worst case error analysis, you lose all this quantitative information, which might be interesting. And secondly, as an engineer, you have certain constraints that you can play with. So if you're looking at the GPS signal on a mobile phone, you can probably allow some level of error some percentage of the time. And if you look at this ninja weapon on the left, which hasn't got a warhead, which was used to kill a few IS militants, you probably have much stricter constraints on the error that your GPS reading can do, right? So as an engineer, you are used to these trade-offs. You're used to allowing yourself a certain leeway in your calculations. So how can we compute these things? So the solution is a tool that I worked on together with my co-authors in 2021. This was a CAF paper, and it's called PAF, for Probabilistic Analysis of Floating Point Arithmetic. And we quantify things like this. Okay? Now, PAF had some limitations. The first one is that it's only an approximate method. And the second one is that it only accepted programs written in a very simple syntax, namely only arithmetic operations. So the purpose of this project was to try to improve PAF because we think we have new techniques to cover not only an extended grammar, so we can now cover square roots and if-else statements, and in fact any roots, but we also have a new technique to produce exact output distributions rather than these approximate distributions, these over and under approximations that PAF gave us. So we can compute exact distribution. I'll show you an example in a while. I was skeptical that we would be able to go as far as we went. I'll show you an example at the end. We can compute quite sophisticated, quite complicated, exact closed form output distributions using something called cylindrical algebraic decomposition, which is a technique from real algebraic geometry, and symbology integrations. And we can cover grammar programs that include if-else statements and square roots and any roots. And the nice thing mathematically is that the if-else statements, the guards of the else statements, fit really well with this cylindrical algebraic decomposition picture. It's very nice mathematically. Everything works very nicely together. So here's the example. This program has less than 10 variables, and we can compute the output distribution for for this kind of program. This is a program that has if-else statements, it has square roots, and it has arithmetic operations. And you can see the shape of the output PDF for one of the quaternions that this returns. It's quite a complicated PDF, but we can compute these things usually in exact closed form solutions using symbolic integration. So I'm going to leave it there. We have an implementation of a tool called PyCAD, which interfaces with the traditional library to do CAD was written in C in the 90s. It's still the gold standard, but we've written a tool to interface with this in Python, which I think might be useful for the community as a whole. And it also allows you to integrate a density function with respect to this CAD. And then we have a new version of PATH that is also under development. So thank you for your attention, and thank you to VeTSS.
Given that we're I'm sorry. Given that we're quite behind on time, we might just move on to the next talk, and people can come to you during the lunch break.
Hello, and thank you. Do I have a broad range here? I hope I do. This is a slightly unusual project for VeTSS. It's at VTRL level 1, maybe 0.5. Very far from actually being technically implementable, but I hope it reveals some things that maybe are not that well known about where program logics come from. So this actually, there should be another logo, there should be the RA logo as well, because this started as an RA internship over the summer. It's mostly been carried out by my Master's by Research student, Piotr Kozicki. Where's Piotr? Hello. Who will start a PhD with me in September. I have very little time, so I'll try to keep the category theory to a minimum. And shouldn't you be thankful for that? Okay, so something that is not as well appreciated as it should be is that most program logics come from some kind of categorical duality. So categorical duality is you've got two categories, and up to a weak sense, they are the same category. So that's the one you first hear when you learn some category theory, and you're like, this is complete nonsense, clearly. Like, I've never heard of this. This doesn't mean anything. If you take the category of sets and functions, and you flip it over, that's actually the same as the category of complete, atomic, Boolean algebras. Okay, this is one of those nonsense things, but actually, I claim that if you look at what it does, it's actually the root of all, like this is what Dijkstra and Tony Hall, the late Sir Tony Hall, did. What does this function do? It takes a set X, you can think of this as a set of states, into the power set of X. Now the power set of X has all the nice operations of logic. It has union, intersection, has all the nice things. So essentially you flip the category over, and suddenly you get a logic. And this is a phenomenon in logic, in algebraic logic. You can see it everywhere. It goes up to Topos theory, it goes to strange places. But I asked myself a very simple question at some point. Okay, so you've got sets. Those are the states of your system. You've got functions. Functions map the states onto some other system. But often we don't have that. We have relations. We have things like bisimulations. We have all sorts of structured relationships between systems. I mean, if you look at COMSERT, what is it but a sequence of 14 proofs of a simulation going layer to layer to layer? So could we somehow learn something from the category theory here? And I gave this to Piotr just to sort of haze him into research. And somehow we worked it out. So, of course, there are, as I said, many morphisms of interest. Many of them are relations. Bisimulations are everywhere in verified compilation and process calculi. If you look at the category rel, though, the second thing you learn about category theory is that if you flip rel over, it's itself. Relations don't have a direction. But we found another way, actually. We have been able to characterize rel op as a certain kind of relations between complete atomic Boolean algebras. So, is that the same as rel? Yes, it is. Is it the same as rel op? Yes, it is. But the difference is it gives us logic. And we even refined that to transition systems and bisimulations. They turn into complete atomic Boolean algebras, known as cabbers. I don't like that because it reminds me of cabbage, but cabbers, with a modality and something called a bisimulatory relation. Okay, I'll just quickly flash a slide in front of your eyes of what a logical system based on this would look like. So what do you have? For every bisimulation, you get a relation between logics on different systems. So R is the bisimulation you can see up there. The slanted arrow is the relation. phi and psi belong to our formulas over different systems. That's the interesting thing here. Well, maybe interesting. So, for example, if phi relates to psi, and then phi prime implies phi, and psi implies psi prime, then you can weaken on the right and strengthen on the left. And you should, if you squint at this, it's just poor logic. You also have disjunction on the left distributes. You can compose bisimulations and then have this functorial judgment. If phi implies psi, then the identity bisimulation, always bisimulation, relates those two, and you also have some modalities. The interesting revelation was the rule on the bottom right, which is, we call this a half adjoint rule, because it looks a bit like an adjunction. I could read down the intuitive meaning of this, but it would take quite a long time. If you want to know more about it, ask me about it. And that is pretty much a very, very quick tour. This has been accepted at FSCD, and you can find the preprint on archive 2605 06533.
Thank you, Alex. There's actually some time for questions if you wanted to. Yeah. I mean, it was very
I
understandable.
can take one aggressive anti-category theory question.
So here's one.
So how far can you generalize it in terms of transition systems? Can you generalize it to arbitrary coalgebras for weak pullback preserving functors, or?
Yes, but that will take the next 2 to 3 years. But we believe that such a duality does exist.
Due to the transitivity. Very
Yeah.
nice.
But we've focused on more structural things. So, for example, secretly, what this functor does, if you look at the version on RHEL, it's the lower lifting of relations. So you have a relation between two sets, you raise it to the power sets by saying everything in the right is simulated by something on the left. And if you set up Cabarel right, this becomes an equivalence. That's something that somehow was missed, even though it's, in retrospect, completely obvious, nowhere to be found in the literature. We've thought a lot about the Egli-Milner liftings, all the other liftings that people might want to do, and we've found some things. I'm not sure I understand them yet. You should talk to Piotr, who understands them a lot better than me.
And I guess also a very nice potential generalization would be to, instead of just looking at relations, would be to go into quantile valued generalization.
I think so yet, but that's beyond our current state of the art.
Thank you very much.
Thank you very much.
Great. We've got time for one more question, actually. You were so fast. Yeah. Anyone?
I tried my best.
Okay, so one from Nolan.
What do the modalities mean? What do they do?
Okay, this is part of my gripe with modal logic. The black diamond is like the diamond you know, but in the opposite direction. It says if you go a step back, phi was true. The reason to have them this way is that, and not to have the white diamond, is that the black diamond is always left adjoint to the white box. So you get a perfect duality. In reality, you always have 4 modalities. It's just that modal logic developed a certain way historically, and it's not, in category theorist terms, the right thing.
So in the crypt key semantics, like there exists a world, but it's in ROP.
Yeah,
Okay.
yeah, that's exactly it. And you can have 4. There's also, the white diamond has a right adjoint, the black box. So you always have 4 modalities in crypt key semantics.
Nice.
Thank you. Not mine. Discovered in 2010, believe it or not. It took a very, very long time for people to realize that this is the thing.
Okay.
Thank you very much.
Thank you. Yeah.
Wow, this is going to be a steep transition from the previous talk, but well. So, my name is Arindam, and I'll be giving a short update on what we have been doing on this project on secure code generation with large language models that has been funding me for the past year or so now. This is joint work with Christina and Henry on TreeCoder, which is our framework and our attempt at bringing in the sort of fragmented field of constraint decoding together. And this is supposed to appear at PLDI in a month or so. So why do we need this framework? And I think I can make a pretty good argument that by experience or through various research papers, prompts do not actually enforce properties. So you ask something within a prompt, and it basically, you're at the whim of the language model. And that is especially true and in fact more insidious for programs. So this might not necessarily be the case now, given that so much development has gone into large frontier language models in the past 6 or so months. But for small language models, this is still a big problem. They are really bad with such properties. And there's a good case for using small language models, and we believe that this is going to increase in the future, especially with heavy use of language model-based coding. So why are they useful? They're attractive because they're local. You can run it privately. They're low cost. And with all these good things comes the issue that they're worse at following prompt instructions. So how do we solve this? There's been enough research in this area known as constraint decoding. So the way language model works is that the final layer of the language model, known as a decoder, generates token one at a time. And this is where essentially you can embed in constraints which are taken out of the prompts and put into this generation loop. So as the tokens are being generated, you can essentially check which direction you're going with regards to some form of correctness embedded by the constraints. And that is called constraint decoding. So the idea is that instead of validating the entire output as to whether it's correct or not, which would be quite wasteful and slow, we sort of embed these constraints at the decoding stage. So as the model goes through the solution space by generating one token at a time, sampling from a distribution, we can embed these constraints over the partial generation. So if you imagine like a partial program or a partial string in a grammar, you can essentially ask the model how far are we on its path of producing a correct, given the constraints, output, and then modify its direction. So that's what constraint decoding means. So why did we build TreeCoder? Primarily, constraint decoding seems like a reasonable solution for security properties, for generating programs that follow certain semantic constraints. It could be something as simple as not using certain functions, or something as complex as source sync relations, etc. So when we started looking into constraint decoding, we realized that the works are quite fragmented. In particular, what it means is that the key choices within this constraint decoding loop are all made in quite an ad hoc manner, which is specific to a particular problem or a domain, and it's really hard to compare these various components. For instance, you can have what sort of constraints you're going to put. So there could be something as simple as syntactic grammar-based constraints, or something as complex as semantic constraints that talks about the entire semantics of the program that is being generated. What sort of decoding strategy are you going to use? How much time are you going to invest? What hyperparameters are going to be used? And all of these have been developed for different techniques, but it's really hard to compare or make a decision on which strategy to use. And that's the question that we found ourselves asking. So if we are going to embed security constraints within this decoding loop, which decoding strategy would work better? How much time do we need to spend doing this? What should the hyperparameters be? And with this question, we realized that there's room for sort of a shared abstraction, and that's what TreeCoder gives. So how does it do it? It essentially, like a good abstraction, separates the machinery. It separates various components into one shared decoding tree. So essentially, it's a tree where every state stores the partial completions that we have seen till now, and with each shared state we have notes essentially representing what we have seen till now. We also store the constraint state, so how far are we on the path of satisfying constraints if possible, and we also store whether the nodes are active, terminal, what you want to expand, etc. And then from this point we can plug in pieces, so we can have a choice over decoding strategies, whether we want to sample, whether we want to beam search, which is by maintaining a certain beam of next tokens, something as complex as sequential Monte Carlo or Monte Carlo tree search, which I won't get into now, but this allows us a handle on decoding strategies. Not only that, we can also sort of compare various different constraints and play around with it essentially by embedding something as simple as syntax constraints, where a program must start with def and then not proceed to add any capital letter words. This is particular. This is just a random example. It was quite useful as a constraint that we played around with, or for SQL aliases, or something as complex as Rust analyzers, where we can call at each partial stage the Rust analyzer and get hints from it and decide what the most promising next tokens look like. And with termination aggregation and optimization as well, you can imagine running an optimizer over all of these sort of hyperparameter and pluggable pieces and figuring out the best constraints with the decoding strategies and the timing budget for your particular task. And that is exactly what we needed as a framework, so that we can then build on top of it by adding more complex security constraints on it. So what did we find? We found that for mostly basic Python programs on a language more or less small as Code Llama, we could almost double by adding very simple constraints. That was true for Rust, since mostly basic Python programs were Python. And for more complex benchmarks, we were able to see improvements with constraints like unit tests and all. But the more important key takeaway here was the fact that we can now compare all of these fragmented design decisions and hyperparameters and see which ones work best for the particular use case. So the immediate next step for this would be that we would be plugging in the security constraints, and that comes with its own host of questions and problems about what security constraints can we plug in, how complex can these constraints be, if it only reasons about the entire program, is it even possible to talk about these constraints when only a partial program is available, which is the case for decoding, and so on and so forth, including how much of these hyperparameters can be optimized for the particular constraints that we're looking at. So that'd be the presentation. I'll be happy to take more questions.
Okay, a question from Alistair.
Thanks, Aaron. That sounds like a really interesting project. I guess my question was about the thing you mentioned at the very end, which is when you're decoding, you only have a sequence of tokens. You don't have a complete program. You don't even have a complete partial parse of a program. Mm-hmm. So I just wondered, that must rule out a lot of things that you could use.
Right, yes. So on one end of the spectrum, if we consider properties that it would only make sense to talk about those properties once we have seen the entire program. For instance, like return codes and stuff. Obviously, if we haven't seen the whole program, we won't be able to reason about it. But then certain properties, we can have a notion of like an incremental sort of check as we are seeing the program. So we parse it incrementally, like sort of an incremental parser as we're seeing the program, and we can rule out certain bad traces if we see those traces by running sort of partial analysis on the program that we have seen. Obviously, doing it arbitrarily at like any possible stage is not feasible. So one of the things we did was we would sort of run certain checks lazily at the end of a line or at the end of a statement, or for instance at the end of a loop when it makes sense to do it. And that is obviously depends on the kind of security property that we're talking about. So yeah, you're right. Yeah, doing it for arbitrary properties would probably not make sense, but there are still some properties in the middle where we can, for instance, talk about with partial programs. A very simple example would be like blacklisting certain functions and not using them, and hence moving the trajectory away if we see that function being used.
Great, thank you.
Okay, if there are no more questions, I think we can move on. Thank you.
So I'll talk about translation validation for super optimized cryptographic software, which is the title and is also a lie. So this project is in fact two projects. One is unfunded, and that's the one whose title is there. And the other one is funded. That's the one that I probably will talk about less today. So essentially the starting point of the translation validation work is something a bit earlier than Hanno's talk last year at this event, which was about MLChem native. So the AWS crypto team's implementation of the new post-quantum cryptographic key encapsulation mechanism, which is a very nice formally verified, or at least a pragmatic approach to formally verifying cryptography, which starts from highly verified core, the entity, and very security critical components, but also performance critical components that are implemented in assembly, composed with a bit of C code over it, which is verified to a slightly lesser standard, so essentially memory safety and type safety, and that this a term that Rod Chapman uses to essentially encompass absence of undefined behavior, to get a nice package with a pragmatic approach to security. And one of the things that MLChem Native does is, on that handcrafted bit of assembly code that they write, they then, in addition to doing a full functional correctness proof on it, they then run it through a super optimizer called Slothy, and they just run the proof again, and magically it works. And the reason why it works is because Slothy, the only optimizations that it applies is swapping instructions in a way that doesn't change the data flow graph. And if you have a good enough model of the performance of your chip, then you can actually find nice optimization through pipelining and timing of memory loads and memory stores. And that gives you sometimes a massive increase in performance. On the other hand, why does the proof go through once you swap those things? Well, if you do a big weakest precondition calculus on a bit of straight line program that has the same data flow graph, then the weakest precondition will be the same after you simplify and inline everything. And so the proof just goes through, and it's magical, but it's extremely brittle, right? If you try to do something that is not just swapping instructions in a way that doesn't change the data flow graph, then your proof falls apart, and you lose the assurance that you wanted. And so the starting point of this program was, what happens if we try to do translation validation instead of proof preservation? And so we started from another starting point, which is inside the EasyCrypt interactive theorem prover. We now have a way of moving into a circuit equivalence checking engine, which is powered by AIGs, and try to see, and this is just bit vector, right? So you model your program as a Boolean circuit, and you try to see if they're equivalent using something which is not throw a sat solver at it and wait a couple of weeks. And we started seeing, like, just testing out, can we do actually translation validation on optimizations that are a bit stronger than swapping? And in fact, we can. We can actually do some transformations, not as easy as the proof goes through. But if you use vector instructions, for example, so doing the same operation on 4 words at the same time, then using a very simple way of specifying what operation is done on each of the words, and using simple rewriting, then you can actually move back into a model where you just say those 2 programs are the same. So with very light guidance at the moment from users, but in the end, ultimately from the super optimizer itself, when it says, I've applied this transformation, please deal with it in the proof, then we can recover a translation validation. Now, the reason why I'm talking to you about this is that I want to use this simple problem as a kind of fisheye lens to try and figure out, okay, we've got those 2 different approaches to assurance in cryptographic software. Which one is actually better in terms of certification? Which one will be more likely to be accepted as evidence of the quality of the software that's coming out? And this is the funded activities for this project are going to be a workshop, which we're still in process of finalizing, bringing vendors and regulators and entities that behave like regulators but are not, together in a room, trying to figure out what the regulators actually want from assurance cases in cryptography, and what are vendors actually capable of producing. And from experience, this is a lot more than what the regulators actually expect. The long-term objective of this is to try and get some transparency into certification for cryptography, which at the moment is a very opaque system where the vendor puts the software in the hands of a lab with some documentation, and the less public documentation is available, the harder the lab has, the harder the lab has to work in order to try and find vulnerabilities. And if they don't find vulnerabilities, then the certificate is issued. That's the wrong way of doing things. And so the idea is to try and use this as a way of pushing formal methods a bit more into the certification frameworks, throughout the world, so common criteria, FIPS, and other things, for cryptography only, for things that we have good specifications for, and trying to push that forward with a bit more transparency for users and regulators as well. Thank you. The most important bit, if you do want to participate in that, come to talk to me, because I want to know when you're free.
Any questions for Francois? Okay, well, we actually managed to catch up in terms of timing and everything. So I guess we break for lunch. Just because there are some funders in the room, I just wanted to point out that these were small grants, and I think we achieved a lot over the course of the year. So please do fund more if you can. Okay, well, we break for lunch.